Students, this is segment 4 of lecture 1 and we have been studying set theory in lecture 1. As we know, we studied set theory in our previous classes. Yet, the basic concepts of set theory will be needed throughout the semester in this course. So, we will be remembering all of those concepts in this lecture. Here in segment 4, we'll be recollecting set operations like union, intersection, joint set and disjoint sets, inclusion, exclusion principle, and at last we will see some examples. Okay, here comes union. So, union is a kind of set operation, and let's consider two sets A and B. The union of A and B is denoted by this. Okay, A union B is a set that contains all of the elements of either A or B or both. I repeat, A union B refers to a set that contains each of the elements of either A or B or both. So, if someone claims that X belongs to A union B, it means X belongs to A or X belongs to B. We can see here an example. For example, set A has 1, 2, 3 and set B has 3 and 5. If I ask you to determine A union B, you take all of the elements of either A or B. So 1, 2, 3, 5. So all of the elements will belong to A union B, right? So here we can see that 1, 2, these two elements are from set A. 5, this element belongs to set B, and 3 is from both, right? So this is how we determine A union B, and we can see another example as well. This is set C, where there are X, Y, and D. This is like Z. So C union D will contain each of the elements of either A, either C or D, like X, Y, Z. Very simple, right? So if we wanna see the Venn diagram representation of this operation, union operation, right? What will it look like? So as you know, universal set is graphically represented by a rectangle. Here, in this case, we are considering two sets A and B. So set A will refer to a circle, and here this is another circle. This is set A and this is set B. As we can remember that set A or circle A refers to the region where all of the elements of set A belong, and circle B refers to the region where all of the elements of set B belong. So, if we shade the whole region covered by set A and B, circle A and B, we can claim that this shaded region contains all of the elements that are from either A or B or both, right? So this shaded region refers to the set A union B, right? What about if there were 3 circles or 3 sets? Then we'll express it like this. This is set A, this is B, and this is C. And if you were supposed to determine A union B union C, this whole region covered by circle A, B, and C, shaded here, this whole region would contain all of the elements of either A or B or C. So this shaded region represents A union B union C. So now we know a lot about union. So what about if there are multiple sets like A1, A2, A3 and till AN? How do we denote the union of all of these sets? We denote it like this: union of AI. I equals to 1 up to N. It means that this is the union of all AI, like all of the sets A1, A2, A3 up to AN. Okay, so that was all from the set operation union. Now we will know about another operation, intersection here. So intersection, like the previous one, we are considering set A and B. The intersection of set A and B is denoted by A intersection B. This symbol, right? A intersection B. What is A intersection B? This is a set which contains all of those elements which belong to both of set A and set B. I repeat, A intersection B refers to a set that contains all of the elements that belong to both of set A and set B. So, if someone claims X belongs to A intersection B, it implies that X belongs to A and X must belong to set B. So, if you want to see an example here, A is 100, 101, 102, and here B 99, 100, and 103. So, if you are supposed to determine A intersection B, you will look for the common elements of A and B, and here we get only one element, 100, that is common to both of these sets. So, A intersection B equals to this set, which contains only 100. And you can ask, if there is such a set that has no common element with another set. Here, C and D do not have anything in common. So, C intersection D will have no elements in it. That is, C intersection D equals to an empty set, or this is null. Okay? Okay. So, now we can represent this intersection operation through Venn diagram. This is universal set U, and this is set A, this is set B, and it means all of the elements of set A belong to this region, and all of the elements of set B belong to this circle. Okay, so here the portion I have shaded now belongs to both of these two circles, right? That means the elements which belong to this shaded region will belong to circle A, or will belong to set A, and also it will belong to set B. That means this region refers to that region which contains all of the elements that are common to both of A and B. So this shaded region refers to set A intersection B. And if there were three or more circles, like for example, this is set A, this is set B, and this is set C. A, B, and C. If we were required to determine A intersection B intersection C, we can figure out that this both region belongs to circle A, circle B, and circle C. So in this region, there are some elements which belong to A, B, and C. So this shaded region represents the set A intersection B intersection C. Okay, so what about if there are multiple sets like A1, A2, A3 till AN? How do we denote the intersection of all of these sets? We denote the intersection of all of these sets like this. There will be a giant intersection sign, and intersection of AI, that is I equals to 1 to N, right? Okay. This refers to the intersection of all of the sets starting from A to AN. Okay, so may I ask you a question, that is, what about this diagram? Here this is circle A and circle B, set A, set B. So if I ask you to determine, seeing this diagram, that cardinality of A intersection B equals to what? You first notice that these two circles haven't intersected, right? So there is no common region here. So since there is no common region, there is no common element, and since there is no common element, A intersection B equals to null. So since A intersection B is such a set where there is no element, so cardinality of A intersection B equals to 0, right? Okay. So that's all from the operation intersection. Now we will discuss about the next topic, that is joint set and disjoint sets. So joint sets. Okay, so from the name we can say that joint sets are those sets which share some common elements between them. Okay, the sets which have some shared elements are known as joint sets. So if we consider set A and B, and A equals to 1, 2, 3, B equals to 2, 4, 5, here we have 2 in both of the sets. That means they have a common element, right? Or they share a common element between them. So A intersection B equals to 2. Since there is a common element between these two sets, we can say that A and B are joint sets. If we draw a Venn diagram here, set A and set B. Here in the intersection region there is an element, that is 2, and here there will be 1, 3, and here there will be 4, 5. So since the circles representing the two sets have intersected, that means circle A and B are joint here in this region, or set A and set B are joint sets. Now these joint sets, this is completely opposite to the previous concept. What is it? That is, if two sets have no common elements between them, then those two sets are called disjoint sets. For example, this is 3 and 5, and set B is C, D. Is there any common element between A and B? No. That means A intersection B equals to null. So if we draw a Venn diagram here, this is A and this is B. 3 and 5, and in B there are C, D. So have the circles intersected? No. Since they haven't intersected, that means they do not have any common element. So it means that A and B are disjoint sets. So we can define joint sets and disjoint set depending on a comparatively easier statement, and that is, if A intersection B equals to null, that means there are no common elements between A and B, then the sets are called disjoint sets. And if A intersection B is not equal to null, or A intersection B is not an empty set, that means A and B must have at least one common element. And if A intersection B is not equal to null, then we claim that A and B are two joint sets. So that was all from joint and disjoint sets. Our next topic is very interesting, that is inclusion-exclusion principle. It's a very important formula of set theory, inclusion exclusion principle. So, what does this principle state? This is A union B, cardinality of A union B. It is said to be equal to cardinality of A, cardinality of B, and cardinality of A intersection B. So, can anyone pause this video and try to prove it by yourself? I think there are a lot of students who can prove it yourself. So, what can be the easiest way to prove this statement? I think it will be using a Venn diagram. So, this is set A and this is set B. So, as we know, the whole region covered by A, B, circle A and circle B represents A union B. Okay? Okay? So it means that this whole shaded region refers to the set A union B, right? And here, this is the common region of circle A and circle B. So, according to the definition, this is known as A intersection B, right? So, let's divide this shaded region into 3 subdivisions, and there this blue region or blue subregion and this region, another blue region, and the black region here. Okay, so A union B is divided into 3 subregions, this, and this. So let's assume that this black region has the total number of elements R. It means A intersection B, cardinality of A intersection B is equal to R, right? Okay, and here the left side of A intersection B, this region has P elements in it. This region has P elements in it, and similarly, the region to the right of A intersection B, this region has Q elements in it. Right? So this has P elements, this has R elements, and this has Q elements here. Okay. Now, as we know that this whole covered region refers to A union B, we can say that cardinality of A union B will be equal to P plus R plus Q, right? P plus R plus Q. This is the cardinality of A union B. Can we rewrite this like this here? We have added an R and subtracted an R here. So here is an interesting thing, that is, this is P and this is R. This is P, this is R. If we add both of P and R, we get the total number of elements of circle A, right? P and R, the total number of elements of circle A. And that means P plus R is equal to the cardinality of set A. So here we got P plus R. So this will be equal to cardinality of A. Similarly, Q plus R will be equal to cardinality of set B. This is cardinality of set B, right? And this R was assumed to be cardinality of A intersection B. So here R is cardinality of A intersection B. And see here, we have already proved the inclusion exclusion principle using this Venn diagram. So this is true, and now we'll see the application of inclusion exclusion principle to solving some interesting problems. Okay, so here this is inclusion exclusion principle, and we'll see it and use it. Okay, so we'll have to draw a diagram here. Okay, so let's see, this is our hero alum, Mr. H, and this is Zaid Khan. Okay, this is hero alum and this is Zaid Khan, and it is known that 80% of BRAC University students are fan of hero alum. So 80% of BRAC University students are fan of hero alum, and 60% of BRAC University students are fan of Zaid Khan. Okay, so we can write here that the percentage of the fans of hero alum in BRAC University is 80%. That is cardinality of H equal to 80%. Here you can ask something, what is H? H is a set that refers to the set of fan of hero alum, right? So cardinality of H equals to 80%, and cardinality of Z, or the set of Zaid Khan's follower, the fan, is 60%, right? So that's we know, and it's also known that 40% of BRAC University students are the fan of both hero alum and Zaid Khan. That H intersection Z, right? Both of hero alum and Zaid Khan's fans cardinality is 40%. So if you are asked to determine that what percentage of BRAC University students are either a fan of hero alum or Zaid Khan, it means you will have to determine the cardinality of the set H union Z, right? H union Z, either fan of hero alum or Zaid Khan. The set refers to H union Z, and you will have to determine H union Z, and according to the inclusion exclusion principle, we get that H union Z cardinality is cardinality of H, cardinality of Z minus cardinality of H intersection Z, right? Okay, so as we know, cardinality of H equals to 80%, cardinality of Z equals to 60%, and cardinality of H intersection Z equal to 40%. So from here we get that cardinality of H union Z equals to 100%. That means 100% of bracket students are either a fan of hero alum or Zaid Khan. Okay, so that's how we apply inclusion exclusion principle. Okay, let's move towards another problem where we can use inclusion exclusion principle, right? So it is known that 70% of Brahmanbarian people can make dalgona coffee, and 50% of Brahmanbarian people can make jalapi. And it is also known that 100% of Brahmanbarian people can either make a dalgona coffee or a jalapi. So can I ask you that what percentage of Brahmanbarian people can make both dalgona coffee and jalapi? So let's see the cardinality of dalgona coffee equals to 70% and cardinality of jalebi making people 50%, and it is known that 100% of Brahmanian people make either dalgona coffee or jalebi. That means cardinality of D union J is equal to 100%, and you are required to answer that what percentage of Brahmanian people can make both dalgona coffee and jalebi. So D intersection J equals to what? So from the inclusion exclusion principle, we know that G union J's cardinality equals to this J minus intersection J. So we get here that D intersection J, taking this in the left side, D plus J minus D union J. It means this was 70%, it was 50%, and D union J was 100%. It means total so using inclusion exclusion principle, we can decide that 20% of Brahmanian people can make both dalgona coffee and a jalebi.